Okay, so this is a little introduction to related rates. This entire packet, right, the first page and a little bit here on the second page is just problems that have no context, just pushing around numbers and variables on the page. Okay, if you keep scrolling, you'll see, right, the further examples here talk about throwing a pebble in a pond, pumping air into a balloon, this ladder problem, a water tank, etc., etc. So you can see that we're headed towards some more sophisticated type of problems. And we're going to rely on our ability to differentiate using implicit differentiation, using the chain rule, using whatever derivative rule is necessary to get through today. So, as it says here, related rates refers to a type of problem in which we solve an equation for a missing rate. So, we're used to solve for x or solve for y or whatever, but now we're actually going to be finding a rate. There are typically other rates and regular variables involved in the equation as well. So, for example, let's take this area of a circle, right? Area equals pi r squared. And here is the rate of change of the radius with respect to time. So I know that because it says dr for radius, right? And then the t here stands for time. Okay, so they're giving us the rate that the radius changes is 2. And then we're supposed to find dA dt when r equals 4. Okay, so it's good. We're going to need some of that same implicit differentiation notation that we've used in the past. Meaning, if I take a equals pi r squared and I differentiate this with respect to time, you'll notice I'm going to write d dt this time instead of ddx. And that's dependent upon the fact that these have t's in the bottom. Okay, so if I differentiate with respect to time, it's just a different variable, but I play by the same rules as I do for implicit differentiation. So when I differentiate just the variable a, right, the derivative of a variable, if it's by itself, is just 1, but since a does not match the lowercase t, I have to multiply 1 by its implicit differentiator, right? So 1 times dA dt is just dA dt. And on this side over here, if I'm going to differentiate pi r squared with respect to time, it's not with respect to r, right? So it's not just 2 pi r by bringing the power rule down, right? The pi multiplies through because it's a constant. It's 2 pi r times dr dt because that's implicit as well. Okay, and this is our new statement where we're probably going to do all the solving as it asks us to do. So here it says dr dt is 2. So that means over here in the dr dt spot, I'm going to plug in a 2. It says find dA dt. So that's what's missing. I'm going to leave that as letters, right? Because that's what I'm solving for. And then it says r equals 4. So in that r spot, I'm going to put the 4. And then I can clean this up a little bit to be like dA dt equals 2 times 4 is 8 times 2 is 16. So my answer would be 16 pi. Now there's no units in this problem, so normally we would include units there, but we're just not going to do that for these purposes. We're just trying to get through the symbolic nature of these types of questions. Okay, so example 2 gives us the volume of a sphere, right? You can see that formula there. It tells us the rate of change of the radius and that we're going to be finding dV dt when r equals 3. Okay, so let's start out with same process. V equals 4/3 pi r cubed. I'm going to use my notation to show I'm differentiating this. All right, derivative of a variable by itself is 1. But v is not t, so technically the left side becomes 1 times dV dt, which is just dV dt. Now I'm going to do the power rule on the right side. There's only an r variable there, so if I bring down the 3, I'm going to overdo this one. It's going to look like this. Decrease it by 1, and then multiply by the dr dt. Right? These 3's will cancel, so technically, I'm going to carry this work up here. dV dt is 4 pi r squared times dr dt. Right? So here it says dr dt is 10, so I'm putting that in the dr dt spot, and then it says r equals 3, so I'll put that in r's location, and then dv dt, let's see, oh, 90 times 4, 360 pi. That is our value for dv dt. Now, it doesn't have to be like an area or a volume like we saw in example 1 and 2. Those are just familiar formulas, right? For example, we can take just a sine theta, is equal to a over 6, right? So a being like the opposite, and 6 must be the hypotenuse of this triangle. So let's do the same thing. Let's take sine of theta, which is a over 6, and let's differentiate that, with respect to time. So derivative of sine theta is cosine theta, as you would expect, but it's implicit. So that would be d theta dt. And then a over 6 is a variable over 6. So you can kind of think in your brain that a over 6 is like 1/6 a. So the derivative of 1/6 a, right, is just 1/6. Because it's like that slope, right? And then times dA dt because it is implicit, the derivative there. So now I'm finding d theta dt. So that means that this is going to remain the letter portion of my answers, and then I'm going to plug in everything else as expected. So cosine, it says theta here is pi fourths. So I'm going to do cosine of pi fourths times d theta dt, and then that's 1/6 times, looking here, dA dt is -2. All right, so I know that cosine of pi fourths is root 2 over 2. So if I write it this way and simplify the right side, I can go ahead and solve in this last step by multiplying by the reciprocal, right, to cancel that out. So times 2 over root 2 here as well. And then this leads me to my final statement that d theta dt must equal -2 over 3 root 2. No need to rationalize here in calculus class. So here is your d theta dt evaluation. I'm going to really quickly do number 4. Actually, what I'm going to do is I am going to differentiate it with you, and then I'm going to have you guys solve and see if you can do the algebraic part of it. We have an equation. Okay, you can think of it like a formula or whatever. Z equals 1/2 xy. We have one rate that they're telling us. The rate that x changes, right, with respect to time is -4. The rate that y changes with respect to time is 3. And that we are to find this rate when these two numbers are true. So I'm going to take z equals 1/2 xy, and I am going to differentiate that with respect to time. The left side becomes dz dt, and then the right-hand side, oh boy, this is going to be a product rule. I'm going to group it so that 1/2 x is my first function and that y is my second function. Both are implicit this time. So when I take this derivative using the product rule, right, product rule, it is first times the derivative of y is just dy dt. Notice I'm not writing dy dx like we did before, plus the second function times the derivative of the first, which would just be 1/2, and then times dx dt, because that's implicit as well. Okay. Now, I'm finding dz dt, so actually this side is going to remain my letters or my variable, right? And then I'm going to plug in the other information along the way. 1/2 x is 8. Dy dt is 3. Y, how can I get y? Leave a blank there, times 1/2, and then dx dt is negative 4. I guess I lied when I said I was going to let you guys finish this one because this does have a little wrench into it. So remember, and we did this for implicit differentiation too, that if you have, you know, points on the original function, right, you can use z equal to 1/2 xy to solve for whatever you need. So like if z is 20 and x is 8 and y, you know, is missing, we can set up a little equation using the original to solve for y. So 20 equals 4y. Of course, dividing by 4 tells us that 5 is probably regular y. So I'm now going to truck that little 5 over in here to the missing parentheses. And then again, in our class, you don't have to evaluate this in any way, shape, or form. I will just because it seems easy to do. Negative 20 divided by 2. So it ends up being 2. So my answer is 2 here for number 4. Okay.